Number one, a student performs an experiment with a rod that is free to oscillate in a horizontal plane. Two identical small spheres, each of mass m, are placed at equal distances from the center of the rod. The student records values of the periods of oscillations of the rod t in seconds for different values of the distance of separations of the spheres d in meters. This is the diagram of experiment, and from this position becomes one. Next, the students plot the variations with d of t, keeping m constant. This is the diagram. T against D. T unit second, while D unit meters. Explain why M was kept constant. I have provided my opinion, my answer about this question. This one, you may copy or you may add your opinion into this opinion. And the second one, the student proposes the hypothesis that T is directly proportional to D. Outline whether the graph support this model. Also, I have provided this. State one other feature of the experiment that the student should keep constant. Also, I have provided my answer, my opinion for this question, this one. The student proposes a new hypothesis such that c squared equal AMD squared plus B, where A and B are constants. After analyzing the data for spheres of individual mass 40 grams, the student proposes that t squared equals 3.4 d squared plus 1.5. Calculate A. State your answer with its fundamental SI unit. Right. So if you look this equation and this equation, that AM equal 3.4. Okay, so we can calculate A through this equation, through this similarity. So AM, A is area, M is mass, that is equal 3.4. So A times mass is 40 grams. 40 grams to kilograms is 0.04 kilograms. 0.04 kilograms, 3.4. So A equal 3.4 over 0.04. And if you calculate, the result is 85. Of the unit, or unit, A unit S squared over kilograms M squared. Okay. So this is the unit, kilograms, mass kilogram, and then 3.4 S squared M squared. So it means A, actually A equal 84, 85, I mean, 85 kilograms, 1 minus 2 and second squared, or 85 second squared, kg power minus 1, m power minus 2. The student goes to investigate the relationship proposed in B between T and M, keeping the constant. Sketch the graph expected for this experiment on the axis provided. Right. So if you evaluate the equation that and if you find the intercept point, the intercept point never on on origin, and there is no intercept point on M axis. Okay, the intercept point uh, occurs on T is not in even if M equals zero, if M equals zero, the intercept point occurs on the t-axis. So the graph will be like this. Okay, because if you evaluate the equation, that is the quadratic equation. Number two, in a series of trials to determine the specific latent heat of fusion of water, L water, once ice is added to an insulated container of negligible mass that contains water. The equilibrium temperature of the water is determined when all the ice has melted. The following data are available. Mass of water 0.095 kg, mass of ice 0.025 kg, specific heat capacity of water 4,200 joule per kilogram Kelvin, initial temperature of ice 0.0 degrees Celsius, initial temperature of water 45 degrees Celsius. Average final equilibrium temperature of water 20 plus minus 1 degrees Celsius. 1 degree Celsius is uh, the uncertainty in change of water actually. 1 degree, right? Suggests why some failures of the experiment are stated without uncertainties in their measurements. I have provided my opinion about this question. One, in experiment, the precision of the measurements of for mass and temperature ensures that the results are as accurate as possible. Precision in measuring variables is fundamental to the integrity of any scientific experiment. It ensures that the data collected is as close to the true values as possible, which is essential for making valid interference. So you may add something or you may add your opinion into this explanation. Let's continue. Calculate the percentage uncertainty in the temperature change of the water. Delta water. Delta water is change. Delta T water is change of water temperature. Right. Percentage uncertainty. Percentage uncertainty is equal uncertainty uncertainty in uh, delta T water, okay, or change in water temperature over change in water temperature multiply 100%. Uncertainty is one, this one over change in water is change in water 0 to 0 to 25. 0 to 25 will change in water temperature, okay, from this one, change in temperature from 20 becomes 45. Okay, so the change is 25. So this is 25 multiply 110 is equal 4%. The thermal energy exchange is represented by the equation. This equation show that the value of L water, L water is specific latent heat of fusion of water. Okay. For the experiment is 3.2 multiplied 10 power 5 joule per kilogram. Right. So we have to rearrange this formula because L water will be subject. M water is mass of water 0.095 kg. C water is specific heat capacity of water 4,200 joule per kilogram Kelvin. Delta T water is temperature change. Just now I have shown you that the change temperature is 25, 20 to 45. And M ice is mass of ice. Mass of ice is 0.025. What else? L water is the subject. Sea water is the specific heat capacity of water, 4,200. And delta T ice is 20 degrees Celsius, change of temperature of ice. So if L water is the subject, this formula becomes, wait, I have to verify. I have to M water over M ice, L water plus C ice, okay? So it means L water equal M water delta T water over M ice minus this one, minus this term, delta T ice, okay? So L water is equal mass of water 0.095. So L water is derived from this formula, becomes this one. And then after that, multiply seawater, specific heat capacity, 4,200. Delta T water is 25, 20 to 45 over mass mass of ice is 0.025 kg multiply sorry, minus, not multiply, I mean minus sea seawater. Seawater is 4,200 CW and delta T ice is 20. Okay, and if you calculate, the result is 315,000 joule joule per kg. Or in this insignificant figure is 3.15 times 10 power 5 joule kg power minus 1. Or you may round it to 3.2 times 10 power 5 joule kg power minus 1. The propagated percentage uncertainty in L water is 6.4%. Calculate the absolute uncertainty, state the value with an appropriate number of significant figures, right? So absolute uncertainty, right? Absolute uncertainty equal percentage uncertainty multiply LW, L water over 100. And it equal, this is percentage uncertainty is this one, 6.4. LW, L water, we already calculate this, the previous calculation. This one, 3.5, 3.2, 3.2, 10 power 5 over 100. And if you calculate, the result is 0.064, 6.4 over 100, 3.2, 10 power 5 here. And it equal 20,480 joule per kg. In significant figure, 2.048. Rounded to 2.0 times 10 power 4 joule kg. But this is for 0 here. Okay. So the absolute uncertainty is 2.0 times 10 power 4 joule per kg. Discuss the effect of ignoring the mass of the container on the final calculated value of L water of specific latent heat of ocean of water. I have explanation about this question and so on. You may copy or you may add something about your opinion into this explanation. Number 3, an electron is moving towards a laboratory on Earth where there is an observer X and a magnetic field. The observer X and the magnetic field are at rest with respect to the laboratory. The path of the electron is deflected by the interaction with the magnetic field. A second observer Y moves at the same velocity as the electron. Explain why observer Y is at rest in the reference frame of the electron. I have provided my briefly explanation, my briefly opinion about this question. One, you may add your opinion here, or you may add your uh, explanation into this, or you may copy this briefly explanation. Outline how observer Y accounts for the deflections of the electron. As well, I have provided, and I will not to reading this. You may copy or adding your opinion. The electron approaches observer X at a speed of 1.8 times 10 power 8 meter per second. A second electron is approaching observer X from the same direction at a speed of 1.5 times 10 power 8 meter per second. Calculate in terms of c. C is speed of light. The approaching speed of the second electron as measured by observer Y. All right. We need to use the relativistic velocity addition formula. And its formula says that Vxn is equal V2 minus V1 over 1 minus V1 V2 over C squared. Vxn is the speed of second electron as measured by observer Y is Vxn. V2 is the speed of the second electron relative to observer X. This V2 and V1 is the speed of the first electron relative to observer X. 1 minus V1, V2, and this is C is speed of light. Right. So V2 is 1.5. So what? 1.50 times 10 power 8 minus 1.80 times 10 power 8 over 1 minus 1.50 times 10 power 8, 1.80 times 10 power 8 over speed of light is 3.0 times 10 power 8 squared. Okay. It becomes minus 0.3 times 10 power 8 over 1 minus, if you multiply this, 2.7, 10 power 8, 10 power 16, I mean, not 8, because 8 plus 8 is 16. And this is 9, 10 power 16, divide. I'm going to writing becomes, according to significant figures, that minus 3.0 times 10 power 7, 1 minus 0.3, right? And the result is minus 4.29 times 10 power 7 meter per second, right? But the speed of the second electron as measured observer, by observer Y is this one, modulus Vxn. Okay, so because speed, and then if modulus, it means this number becomes positive. So it becomes positive 4.29 times 10 power 7 meter per second. No, we are going to express this result in terms of C. In terms of C, it means divided by C, divided by speed of light. So V Xn is equal 4.29 10 power 7 over 3.0 10 power 8 meter per second. It's meter per second. So it's going to be, if you divide, the result is 0.143 C. State one example of the paradigm shift resulting from the Lorentz transformation. I have provided my briefly opinion about this question. This one, you may copy or you may add your opinion into this explanation. Number four, a spaceship travels from Earth to the orbit of Mars with a constant velocity of 0.4 c. The distance traveled by the spaceship is 2.0 multiplied 10 power 8 kilometers, as determined by an observer on Earth. Calculate in kilometers, unit in kilometers, the distance traveled as measured by an observer in spaceship. Right. Uh, we are going to using the Lorentz factor formula. Okay. And distance equal d0 over gamma. D0 is distance as measured by the observer on Earth. This one. And gamma is the Lorentz factor. So the first step, we need to find the Lorentz factor. Okay, Lorentz factor formula is 1 over square root 1 minus v squared over c squared. V is constant velocity. This one. Constant velocity 0.4 c. C is speed-like. So if phi equals 0.4, substitute into this formula, it becomes 1 over square root 1 minus 0.4 squared 0.16 c squared over c squared 1 over square root 1 minus 0.16, and it is 1 over square root 0.84. And if you calculate, the result is 1.091. Round off to 1.09. Okay. Now, substitute this result, gamma, into this equation. So d, or distance, equal, d0 is 2 point, this one, distance traveled by the spaceship, 10 power 8 kilometers over this number, 1.09. And if you calculate, the result is 1.835. 10 power 8 kilometers, round off to 1.8. These significant figures. Next, while the spaceship is traveling, a radio signal is sent from Earth to the spaceship when it is at 3.0 times 10 power 6 kilometer as measured from Earth. Show that according to an Earth observer, the time taken for the signal to reach the spaceship is about 17 seconds. The effective speed of the radio signal from the perspective of an observer on Earth is, I'm going to using term VE. Okay, VE equal C minus VS. Okay, E. Okay, yeah. And VE is effective speed, C is speed of light, and Vs is speed of spaceship. Ve equal C minus 0.4 C because Vs, and it is 0.6 C. C is speed of light. We can convert 0.6 times 3.0 times 10 power 5 kilometer per second, and the result is 1.8 and 0.5 kilometer per second. Now, the time taken for the signal to reach the spaceship, but we are going to using the formula delta t equal, sorry, this is d, delta t equal d over c minus v. This is the distance traveled by the signal in the Earth frame. This d, okay. C is the speed of light, and v velocity of the spaceship. Delta t is the time travel. So it's going to be 3.0 times 10 power 6 over 3.0 times 10 power 5 kilometer per second, 0.4, going to using dot. 0.4 times 3.0 times 10 power 5. And if you calculate the result is 16.67. Sorry, round off becomes 17, sorry, 17 seconds. Determine according to an observer in the spaceship the time taken for the signal to reach the spaceship. All right. So we're going to find the time taken, delta t x and equal gamma times delta t minus v times delta x over c squared. This is 1.09. Delta t is 16.7 minus v is 0.4 second times 0.4, sorry, not second, 0.4 c, I mean. 0.4 c, this one, 0.4 c. And delta x is the distance uh, between the Earth and the spaceship when the signal is sent. So it means delta x equals c times 16.7. So delta x equals C times delta t. So it is over square root, it's over C squared. So divide C 1.09, 16.7, uh, minus 0.4 times 16.7. And if you calculate, the result is 10.92, round off to 11 seconds. Number 5, four events A, B, C, and D are plotted on the space-time diagram. The city x-axis are drawn in the reference frame of observer P. Observer Q is moving with respect to P. The city x-axis for observer Q and the path of a beam of light L are shown. The scale on both axes is the same. When I said the scale, this is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, right. Determine the speed of observer Q with respect to observer P. The city-action axis of observer Q passes through the points, the coordinate points, origin 0, 0, here, this one, and 3, 5. Wait, 3, 5, right, this one, okay? And then to find the speed of observer Q relative to observer P, we can use the slope of the city, this line, city action axis. The slope of city action axis uh, based on the coordinate is city action over x. So slope, I'm gonna write it here. Slope to now 3.5 y over x, it means 5 c3 is equal ct xn over x, like that. And the speed of observer q is given by the ratio, but I'm going to writing the speed c of observer q is given by the ratio ct xn of x equal c over 3 c over v. The slope corresponds to the velocity of observer q, and it can be calculated as tangent theta. Okay, tangent theta. Tangent theta is equal v over c. The velocity of observer q relative to observer p, we can determine using the formula that v over c equal 3 over 5, or v equal 3c over 5, or it equals 0.6 c. Draw and label the x and axis for observer q. The slope, uh, the slope will be minus, okay, minus 3 over 5. If minus 3 over 5, it means uh, 3 is y and 5 is X 1, 2, 3, 4, 5, and then if 5 is 1 or 2 from zero from origin to this one as well, B and to B and D, because B and D has slope or gradient 3 over 5. So you may use your ruler. List the events that occur simultaneously according to observer P. Right. So from the coordinate events, the four events, A, event A has CT coordinates is 3. B has CT coordinate is 0.6. C has CT coordinates 1. And D has CT coordinates is 3. So, what will be here? So according to observer P, events A and D, okay, they have same city coordinates. If even A and D occur simultaneously. Slide. Identify by annotating the diagram which event occurs first according to you. Right. We are going to return to this diagram. So it has the same it has the same slope with this x axis. It means the line through C, okay, and parallel with this with accent line with parallel. You may create the strike line with your ruler. Explain by using the diagram why light from events A and D is received simultaneously by observer Q. Right. But I'm going to show my brief explanation. This is my explanation. And then on the diagram, I'm going to create a straight line through A and D. And look between the city accent line and straight line A and D, there is 45 degrees here. Okay. So the city accent axis represents the observer's time axis in the Q frame. So if you look the information or the explanations on this box. Number 6, a kaon decays into two pions, pion A and pion B, that can be used to determine the rest mass of the kaon. So the decay pion A has a kinetic energy of 210 mega electron volt, and pion B moves in the opposite direction to that of pion A with a kinetic energy of 48 mega electron volt. The following data are available. These are the data. Rest energy of pion A is 150 mega electron volt. Rest energy of pion B is 135 mega electron volt. In the energy, momentum relation, the formula is this one, this equation. Identify the term E, right? I'm going to identify the term E for pion A, for pion A, for pion A. The energy, according to the information, that 140 mega electron volt plus 210 mega electron volt, and it is 350 mega electron volt. While pion B, the energy is 125, 135, I mean, mega electron volt plus 48 mega electron volt, and it is 183 mega electron volt. So the total energy, is equal 350 plus 183. It equals 533 mega electron volt. And I have at my briefly explanation about this, the term E in the energy momentum relation represents the total energy, which is the sum of particle rest energy and kinetic energy. This kinetic energy plus the rest energy. Okay. So the particle rest energy plus kinetic energy is this one, 533 mega electron volt. Show that the total momentum of system is about 2000 mega electron volt per C. The energy momentum relation is this one, according to the information that E squared equal PC squared plus M0 C squared squared. Okay. To solve P, it means we have to rearrange this formula, becomes uh, PC squared, PC squared, PC squared equal E squared minus M0C squared. And then P equals square root E squared minus M0C squared over C. That's the formula. Now, momentum of pion A. Momentum of pion A is PA. So, momentum of pion A. After this, we are going to find the momentum of pion B. And then the total momentum. Momentum of pion A is 35, 350. 350 square, 350 because EA, so 350 EA, okay, so 350, I'm going to write in here, 350 square minus 140 square, okay, because M0C square is 140 over C. Okay. And is equal, if you calculate, the result is 320.78 mega electron volt C power minus 1. And after that, I'm going to use this space. Momentum for pion B. It is square root of 183 squared minus 135 squared over C. And if you calculate, the result is 123.55 mega electron volt C power minus 1. So the total momentum, total P, is 320. This is becomes cell 21, and this one round off to 124. So 321 minus 124 is equal 197 mega electron volt per C, or round off becomes 200 according to this statement. That's what. Calculate in kilograms the rest mass of the kaon. We are going to using the formula according to Einstein formula, that E equal mc squared. Okay, so the rest energy of kaon is rest energy of kaon. It is square root 533 squared minus 197 squared. This is energy minus the energy minus momentum. Okay. And the result, 495.27 mega electron volt. According to this formula, if we are going to find m equal E over C squared. So m kaon is equals energy over C squared, or 495.27 mega electron volt over C squared. Or we can write in for 495.27 mega electron volt C power minus 2. Now we are going to convert this result, this unit, into kilograms. One mega electron volt C power minus 2, it equal 1.7583 times 10 power minus 30 kilograms. This is the conversion. Now it means we are going to calculate this result with this number. So 495.27 times 1.7583 times 10 power minus 30 kilograms. And if you calculate, the result is 883.066 kilograms, rounded to based on the significant figures, sorry, times 10 power times 10 power minus 30. Round off becomes 8.83. 10 power minus 28 kilograms. So mass count in kilogram is 8.83 times 10 power minus 28 kilograms. Number 7, global positioning system GPS rely on the accuracy of clocks on satellites that orbit the Earth. State the equivalence principle. I have provided my briefly explanation. This one, you may copy or you may add something from your opinion for this explanation. Next, B, spatial and general relativistic effects must be considered when correcting signals from the clocks for GPS applications. Explain, in relation to general relativity, why these corrections need to be applied. I have provided as well my brief explanation. Number 8, a uniform cylinder of mass m and length L has a moment of inertia of 112 ml squared when rotated about an axis through its center. This is the cylinder. Outline what is meant by moment of inertia. I have provided my briefly explanation. You may copy or add something into this explanation. State the conditions for rotational equilibrium as well. I have provided my explanation. Two identical cylinders, each of mass m and length L, are connected end to end. Show that the moment of inertia when these cylinders are rotated about their combined center is 2/3 ml squared. So there are two identical cylinders. If one cylinder, the moment of inertia is 112. If two cylinders, we are going to prove that the moment of inertia is 2/3 ml squared. Okay. If one uh, if one cylinder is 112 ml squared. If two cylinders, two identical cylinders, it means m becomes 2m because 1m plus 1m, as well L becomes 2L, and it's going to be 112 times 2m times 4L squared. 4 times 2 times 1, 812 ml squared. Simplify, it becomes 2/3 ml squared. So same with this statement. Okay, this the diagram to identical cylinder. A two-blade propeller can be modeled using the two-cylinder arrangement in Part A3. The following data for the two-blade propeller are available. Length of its blade 0.60 meters, mass, mass of its blade 2.2 kg, so that the moment of inertia of the two-blade propeller is about 0.5 kilograms meter square. Okay, right. So moment of inertia at the center is I center. Okay, moment of inertia of the center is 112 ml squared based on the previous statement. So if m equal 2.2 and length equal 0.6, it's gonna be 112 times 2.2 times 0.6, and it is 0.066 meters squared. Next, now moment inertia combined is moment inertia at center plus m d squared. It is according to parallel axis theorem. And it becomes 0.066 plus m is 2.2, d is 0.30 squared. And if you calculate, the result is 0.264 kgm squared. And moment inertia total is equal to 2 times combine of moment inertia. I need more space. So it is 2 times 0.528. Okay. Sorry, 0. This is the result. 0. This one, 264. 264. And it is 0.528. This is the result. In kilograms meter squared. And you can simplify, become 0.5 according to the statement. The two-blade propeller is initially at rest when a constant torque of 140 Newton meter acts on the two-blade propeller. It reaches an angular speed of 750 radian per second. Ignore any fractional torque. Calculate the time taken for the two-blade propeller to reach the angular speed 750 radian per second. We are going to use rotational dynamic equation, and according to this equation, according to rotational dynamics, that the equation is tau equal I times alpha. Alpha is the angular acceleration, tau is constant torque, constant torque is 140 Newton meters. And then I is moment inertia. Moment inertia is 0.528 based on our previous calculation. Right. If alpha is the subject, we can rearrange this formula becomes tau over I. And it is 140 over 0.528, and it is 265.15 radian per second squared. Now, we use uh, we use the formula omega equal alpha times theta. We're going to use this formula to find time. This is t. Omega is the final angular velocity. This one, 750 radian per second. And then alpha is the angular acceleration, and t is time. So we have to rearrange this formula becomes t equal omega over alpha. And substitute the information that omega is 265.15 over 750. Okay, so it's going to be, if we calculate, 2.83 seconds. Yeah. Okay, so it needs 2.83 seconds. Next, calculate the number of revolutions of the two-blade propeller to reach the angular speed of 750 radian per second. We will be using rotational kinematic equation that omega squared equal omega 0 squared plus 2 alpha theta. Omega is angular velocity. Omega 0 is initial angular velocity. This is 0 because it's starting from 0. Okay, and then alpha is angular acceleration while theta is angular displacement. So we're going to find theta becomes 2 alpha theta equal omega squared because this is 0. And theta equal omega squared over 2 alpha. So it means omega equal 750 over 2 times 265.15, and the result is 1061.7 radians. Now, one revolution is one revolution is theta over 2 pi. Theta is this one, radians over 2 times 3.14. And if you calculate, the result is 169 revolution. Approximately becomes 170 revolution. The propeller is brought to rest in 5.0 seconds, determine the average value of the external torque applied. We're using kinematic equation that alpha equal omega over t. So alpha equals 750 over 5 because t equals 5. And this is 150 radian per second squared. From Newton's second law, uh, we have a formula that tau equal I times alpha. Torque equal I is the inertia and alpha is the angular acceleration. So tau equal 0.528 times 150 and it is 7.9. Sorry, 79.2 Newton meters. Round off becomes 80 Newton meters. Number 9, a closed system contains 0.0070 mole of an ideal monoatomic gas. The gas undergoes a cycle of 4 steps represented below, consisting of 2 isobaric and 2 adiabatic processes. This is the diagram of isobaric and 2 adiabatic process. Initially, at point A, the gas is a pressure of 120,000 Pascal and a temperature of 200 Kelvin. Show that the volume of the system at point A is about 1.0 times 10 power minus 4 meter cube. We can use the ideal gas law formula to find the volume. And the formula says that PV equal nRT. And if V is the subject, we can rearrange becomes nRT over P. V is volume, N is number of moles, R is the ideal gas constant, T is temperature, and P is pressure. So V equal 0.0070 mole times 8.314. This is the ideal gas constant. And the unit is joule over mole Kelvin. Okay. Times temperature 200 Kelvin over 120 times 10 cube Pascal. And I have calculated the result is 9.7 times 10 power minus 5 meter cube. Or we can round off becomes 1.0 10 power minus 4 meter cube. The gas undergoes an isobaric process from A to B, reaching a volume of 1.3 times 10 power minus 4 meter cube. Show that the temperature of the gas at B is about 270 Kelvin. We can use the ideal gas law as I written, PV equal nRT. When the pressure is constant, and this pressure is constant, we can set up a ratio of the initial and final state becomes like this, PA VA over TA equal PB VB over TB. P for pressure, V for volume, and T for temperature. When isobaric process, it means PA, pressure on A, equal pressure on B, or PA equal PB. So the pressure terms we can cancel out, okay, if PA equal PB because of isobaric process. So this equation being VA over TA equal VB over TB. Now we're going to find TB. If we're going to find TB, it means we have to rearrange this formula. This equation becomes like this. TB equal TA times VB over VA. Substitute the numbers, the data, 200 Kelvin. Okay, VB is this one, 1.3 times 10 power minus 4 m cubed. And then VA is this one, taken this one, 9.7, 10 power minus 5 m cubed. And the result is 26.8 times 10 Kelvin, or 268 Kelvin, or round off becomes 270 Kelvin. Same with this statement. The gas now undergoes an adiabatic compression from B to C. For this compression, the ratio of the pressure is pressure at C over pressure at B equal 5. Determine the volume of the gas at C. Right. For an ideal monatomic gas and the relationship between pressure and volume, we have an equation. Equation is PV, PV power gamma equal constant. Its gamma is 5/3. So if gamma is 5/3, it means becomes PV power 5/3 equal constant. Gamma is 5/3 because gamma is the adiabatic index for a monoatomic ideal gas. So 5/3 is the index of adiabatics monoatomic ideal gas, right? And when PC, when PC over PB equal 5, it means PB over PC is 1/5. Okay. So the equation for an equation for an adiabatic process is like this. I would like to write in PB VB power gamma equal PC VC power gamma, right? If you are going to find VC, it means we have to rearrange this formula becomes VC power gamma equal PB VB power gamma over PC. Right. So gamma is 5/3, so it means VC power 5/3 equal PB VB power 5/3 over PC. Okay. And I would like to create becomes uh, the left hand side and the right hand side give power 3/5, also power 3/5. If I arrange like that, this equation becomes Vc uh, equal with Pb over Pc power 3/5 times Vb because it equal 1 power 1. Next, so Vc, Pb over Pc is 1/5, 1/5 power 3/5, okay? And Vb is 1, Vb, Vb is this 1.3 times 10 power minus 4. 1.3 times 10 power minus 4. Okay, so Vc equal, if you calculate, the result will be like this, 0.494 times 10 power minus 4 meter cube. Okay, or in significant figures, 4.9 times 10 power minus 5 meter cube. Next, identify the nature of the thermal energy transfer, Q. The change in internal energy of the gas, delta U, and the work done, W, for each step of the cycle. Insert in the table below plus to identify a positive value, negative to identify a negative value, or zero when the quantity does not change. Three values are given. Next, the first column. I will start with change in Q, or thermal energy transfer in Q. In an isobaric, uh, sorry, A to B, I mean change in Q of A to B, isobaric expansion from A to B. In an isobaric process, heat is added to the system to increase the internal energy and do work. When the gas expands, the thermal energy transferred to the system is positive. So it means Q will be greater than 0, and the sign is positive. Now, how about change in U or delta U? This is delta U, this one, according to this information. Delta U is about change in internal energy. Okay, delta U. The change in internal energy is related to the change in the temperature. When the temperature increases, the thermal energy also increases. If it increases, it means delta U will be greater than 0. Greater than 0, it means the sign is positive. Work done already positive. Next, the second column. The second column, uh, or the second process, is the adiabatic compression from B to C. Change in Q, or thermal energy transferred in Q equal 0. Equal 0, it means does not change. Next, we move to this one, the change in U or delta U, change in internal energy. When there is no heat exchange, any change in internal energy comes from the work done. In adiabatic compression, the gas is compressed, so the internal energy will be increased. If the internal energy increases, it means delta U greater than zero. If greater than zero, the sign is positive because greater than zero. Now, the next about work done. Work is done on the gas, which result in a positive amount of work being done on the gas. So the work done is negative. If negative, it means work done less than zero, less than zero negative. The third process or the third column, this is isobaric compression from C to D. Now, about thermal energy transfer, Q, change in Q. In an isobaric process, heat is removed to compress the gas. So the thermal energy is transferred out of the system. The transfer out of the system, it means Q less than zero, the sign is negative. Next, this one, delta U or change in U or change in internal energy. As the gas is compressed, the temperature will be decreases. So the internal energy also decreases. If the internal energy decreases as this information, delta U will be less than zero and the sign is negative. Now work done. The work is done during a compression is the formula is or the equation W equal pressure times delta V. When the volume or delta V decrease uh, and the gas compress, the work is done will be on the gas. So it means W or work done less than zero. If less than zero, according to this formation, the sign is minus or negative. Now, the fourth process or the fourth column, this is the adiabatic expansion from D to A. The first column, change in Q or thermal energy transfer Q. In adiabatic process, no heat is exchanged with the surroundings. So it means Q will be zero because does not change. Now this one, delta U or change in U, change in internal energy. When the gas expanding adiabatically, it does work on the surroundings and its internal energy will be decreased. So that's why the sign will be negative here because delta U less than zero, the sign is negative. Now the last, work done. The work is done by the gas expansion. So the work done will be greater than zero. If greater than zero, the sign is positive, like this. Next. Deduce without performing any calculation that during the cycle ABCDA, there is a not output of thermal energy. I have provided my briefly explanation about this question, and this is my brief explanation. You may add something or you may copy my briefly explanation. Next, discuss in terms of entropy changes, the impact of this cycle on the surroundings. As well, I have provided my briefly explanations about this question. This one, you may copy or you may add something on my briefly explanation. Then, a bubble of gas is rising at constant speed in a container filled with a liquid, so that the speed of the bubble can be estimated as this equation, where R is the radius of the bubble, rho is the density of the liquid, and eta is the viscosity of the liquid. Assume the weight of the bubble is negligible. Right. When a bubble rises through a liquid, three main factors acting on it actually. The first, the first is buoyant force. Buoyant force, I would like to writing buoyant force. Okay. Okay, buoyant force. What is buoyant force? Buoyant force is the force acting upwards due to the liquid's density. And the second force is gravitational force, or Fg. The gravitational force is force acting downwards, so buoyant force to upwards, while gravitational force is to downward. Gravitational force because the weight of the liquid displaced by the bubble. And the third force is drag force, Fd. Drag force is a force acting downwards as well. Drag force is occur because the liquid's viscosity opposing the bubble's motion. Okay. Now, we can state there's three forces in an equation, and the equation is Fb equal Fg plus Fd. Right. For simplicity, uh, we assume that the weight of the gas bubble is negligible. So it means the gravitational force can be ignored. If the gravitational force can be ignored, it means this equation being Fb equal Fd. Right. It means buoyant force equal the drag force. Now, we can determine the buoyant force through Archimedes' principle that buoyant force equal rho times the gravitational force times phi. Right. Rho is density, g is gravitational force, phi is volume. If spherical bubble volume is phi, spherical volume is 4/3 pi r cube. We can substitute into this formula. So Fb becomes, buoyant force becomes rho times g times 4/3 pi r cube. That is for buoyant force. Now, it's for buoyant force. The second, drag force. We can determine drag force according to Stokes' law. And the formula is Ft equal 6 pi eta r phi, right? Eta is the dynamic viscosity of the liquid, while phi is the terminal velocity, not volume. This is phi for terminal velocity. Okay, so different with phi. This phi is phi for volume. This phi is phi for the terminal velocity. Now, Fb equal Fd. Fb equal Fd. It means rho g for 3 pi r cube equals 1, 6 pi eta r v. Pi over divided by pi equal 1. And this formula we can rearrange because we are going to find v, velocity, like this equation. So it's gonna be, I would like to writing for third rho g r cubed equals 6 eta r v, like that. So v equal 4 third over 6 rho g r cubed over eta r of here. So phi is this one r divided by r. It becomes r squared. 4 third over 6 becomes 4 over 18. Rho g r squared over eta, like that. Now simplify 4 over 18 becomes 2 nins rho g r squared over eta, or phi equal to r squared, that's 1 rho g over 9 over 9 eta, like that. So same with this statement. Next, the velocity of the bubble is measured to be 18 centimeter per second. The radius of the bubble is 0.45 millimeters, and the density of the liquid is 1,300 kilogram per meter cube. Calculate in Pascal second the viscosity of the liquid. So we are going to find eta. So we have to rearrange this formula. If we rearrange this formula, it becomes 9 eta equal to r squared rho g over phi, or we can move 9 like this. Eta equal to r squared rho g over 9 phi, right? But I would like to convert the velocity phi from 18 centimeters per second. So better writing here, phi equal centimeter becomes meter, because this is the density is in meter cube. So we are going to convert centimeters to meters. Meter becomes divided by 100. It's going to be 0.18 meter per second. Right. That is for velocity. And as well, millimeter, the radius r. Better here. R is 0.45 millimeters. Convert to meters, it's going to be 0.45 times 10 power minus 3 meters. This is 4, right? Okay, now we are going to substitute into this formula. So eta equal 2 times this one, 0.45, 10 minus 3 squared, because r squared, and then times rho is 1,300, g is 9.8. over 9 times 0.18. This one. So if you calculate, the result is 3,185 10 power minus 6 Pascal second. Or you can writing in decimal 0.00385 Pascal second, or it is 0.0032 Pascal second. Like that. Justify with a calculation that laminar for laminar flow applies in this situation. Okay, to justify that laminar flow applies, we need to check the Reynolds number or RE. This is symbol of Reynolds number. Reynolds number can determine whether the flow is laminar or turbulent. To calculate the Reynolds number, we can use the formula Reynolds number equal rho phi d over eta. Okay. Eta is the viscosity of liquid. Rho is density of the liquid. D is diameter. Okay, diameter of bubble. And V is the velocity of the bubble. This V not volume but velocity. But I would like to calculate diameter first. The diameter of the bubble is 2 times R radius. So 2 times 0.45 times 10 power minus 3. And it is 0.0009 meters. Now substitute into this formula becomes Reynolds number equal 1,300 times 0.18, the velocity 0.0009 meters over 0. This number is this one 0.003185. 0.03185. And if you calculate, the result is 66.12. So what it means, this number, this result? Flow is considered laminar if the Reynolds number is less than 2000. So laminar if Reynolds number less than 2000. Okay. Our calculation is 166.12 is less than 2000. So we can conclude that the flow is indeed laminar. The conclusion that the flow is indeed laminar. Laminar in this situation. So if the flow indeed laminar in this situation, it means the assumptions and all calculations we have made are valid. So the uh, calculation, the calculations and as well assumption are valid. Number 11, a child is on a swing. The child is displaced to one side through a vertical height of 1.0 meters above the rest positions of the swing. The swing is released and reaches h equal 0.70 meters after a complete oscillation. So the first positions when this child at 1.0 meters, and after one oscillation, uh, her height is 0.7 meters. Determine the Q factor. The Q factor we can determine through um, uh, for one oscillation is 2 pi times the number of oscillation. Number of oscillation is 1. That's 1 over the high loss. The high loss is 1 minus 0.7. And if you calculate the result is 20.93. Or round off becomes 21. So that is the Q factor. The period of the swing is 3 seconds. That's one period, 3 seconds. Draw the variations with time t of the high h for the first two complete oscillations. Two complete oscillations, it means if one oscillation is 3, or one period is 3, it means if two complete oscillations is 6. Okay, right. So it started from 1, okay, 1 to when it positions at rest is 1.5 here, second. And when 3 seconds, the positions on 0.7 here, 0.7. And after that, 4.5 seconds, it rests here. And now we are going to determine h here. So I'm going to using 0.7 power. If 6 seconds, it means 6 third, because one period is 3. So at 6 seconds, it means 0.7 power 6 third, and it is 0.49. 0.49, it means 0.5, a round of 0.5. So it's going to 0.5 here. Okay. Estimate the height reached by the swing after 15 seconds. After 15 seconds, the height equals 0.7 over 15 third, 0. Sorry, 0.7 power 5. And if you calculate, the result is 0.168, or round off becomes 0.17. In one arrangement, an image that is half the height of the real object is produced by a lens of focal length f. Deduce by calculation and in terms of f the position of the object when a converging lens is used, right? So the magnification produced by the lens is given by n This is the formula. Okay, I'm going to use in the black color. Okay, M equal uh, image height or phi minus phi over the object height is u, or the image distance over the object distance, can like that. And it's equal, according to this information, that it's equal minus half. Right. So it means the implication is we can write in that the another equation that phi phi or the image equal equal half, okay, 1/2 times u times object. U is object, phi is image. Right. So, and after that, substitute phi equal 1/2 u into the equation, this one over f equal 1 over u plus 1 over phi. And it's going to be 1 over f equal 1 over u plus 1 over u half. This one, actually phi is u half. And it becomes 1 over f equal 1 over u plus 2 over u. So 1 over f equal 1 plus 2, 3 over u, or u equal 3f. So the position of the object is u equal 3f. Position of the image, or of the object, is 3 times f, 3 times focus. Right. So a ray diagram to show the arrangements to describe in A part 1, right? 3F, it means 1, 2, 3 here, and the object here. Okay. Can create the strike line. As the ray. Okay. Then through F, sorry, through F is, okay, after that, the next ray, oh, wait, that, and this is the image. Okay, that one. A diverging lens, a focal length 5.0 centimeters, is now used to produce an image that is half the height of the object. State the nature of all images formed by a diverging lens. I'm going to writing a couple of them. A diverging lens characteristic for the image are virtual, and then upright, upright, or the different terms is erect, reduce in size, or in different term is diminished, located, on the same side of the object. That. And you may add the image smaller than f. As well, the image smaller than object. Next. Show that the positions of the object is at the focus of the lens. Right. Now, we're going to substitute phi, phi equal u half. Okay. As you know that on this case, m equal half is equal minus phi over u, because this is the different lens, diverging lens. The first one is converging lens. So it means we can state that phi or image is equal minus u half. Now substitute uh, into this equation. Okay, so it's gonna be minus 1/5 equal 1 over u plus minus because it's minus 1 over u half. So it becomes minus 1/5 equal 1 over u minus 2 over u. And it becomes minus 1/5 equal minus 1 over u. So it means u u equal 5. Yeah, u equal 5. So so the object position at 5 centimeters. Okay, or u equal f. U at f. Construct a scale right diagram to show the situation described in B part 2. All right, so U at F, so it means U position here. Yeah, after that we can create the strike line. Okay, and then through F, this is F. Sorry. There, and then after this one is 3. Okay, and this is the image here. Right. A converging lens and a diverging lens are combined to form a visual image of a distant object. The focal point of the converging lens and the focal point of the diverging lens coincide. The diagram shows two rays from the distant object and the formation of the intermediate image I by the converging lens. Construct two other rays to show that the final image is upright or erect, right, through this diagram. So the first step, we need to create the strike line through this intercept point, okay, and the strike line like this, parallel with this line, okay, and it's gonna be wait, right, and after that, the strike line through this point to you may sketch with your ruler. Okay, and this is this is uh, the image that one. Number 13, the focal length of the objective lens of a refracting telescope is 1.1 meters. The telescope is used to observe the moon. The image observed subtends an angle of 0.34 radian. The following data are available. Distance to the moon is 380,000 kilometers. Diameter of the moon is 3,500 kilometers. Calculate in millimeters the focal length of the eyepiece. Okay. First, I'm going to calculate the actual angular size of the moon as seen from Earth. And I'm going to use the symbol is theta. The theta actual is, is equal diameter of the moon 3,500 kilometers over distance of the moon 380,000 kilometers. And if you calculate, the result is 0.0092105 on my calculator, like this. And after that, I'm going to calculate the angular magnification with symbol M. Angular magnification formula is theta observed over theta actual. This is the theta actual. And the theta observed is this one, 0.34 radians over theta actual, 0.0092105. And the result is 36.914286. And the next step, I'm going to calculate the focal length of the eyepiece. The focal length of eyepiece is the focus one, focal length of the objective lens of refracting telescope, 1.1 meters. 1.1 meters over this magnification, 36.914. And the result is 0.029798. This is in meters. So I would like to convert into millimeters. It means this number calculate by 1,000, 1,000 is equal 29.799 millimeters. Round off becomes 30 millimeters. That one. Large optical telescopes are usually reflecting telescopes. State one example of how large reflecting telescopes have led to scientific discoveries. I have provided my explanations, my opinion about this. You may copy or you may add something for your explanation. Next, outline why chromatic aberrations is less significant in reflecting telescopes than in refracting telescopes as well. I have provided my brief explanations. You may copy or you may add something according to your opinion. Next, the third, distinguish between the paths of the light rays in Newtonian mounting and Cassegrain mounting telescopes. I have provided as well. Okay. Number 14, outline how dispersions affect the transmissions of light in an optic fiber. I have provided my explanation, so I will not explain because the durations I have to I have to explain on the calculations. Okay, you may adding something or you may copy these explanations, my opinion. Next. The glass in a 10 kilometer optic fiber has a refractive index that varies between 1.45 to 98 to 1.45 to 64. A pulse of durations is 1.0 nanosecond is transmitted through this optic fiber. Determine the minimum received pulse duration. Right. The first, I'm going to calculate the speed of light in the fiber, right? To calculate the speed of fiber, I'm going to start from for the minimum refractive index and minimum is 1.45264. This one. This is the minimum refractive index. Okay, and this one is the maximum refractive index. All right. So the minimum refractive index, we can determine the velocity or speed. Minimum speed equal 3 times 10 over 8 over 1.45264. It is 2.0652 times 10 over 8 meters per second. Next, for the maximum refractive index, and maximum is 1.45264 4.298. So we can determine the speed maximum. 3 times 10 power 8, speed of light, 1.45298. And the result is 2.0647 times 10 power 8 meters per second. Okay. And after that, I would like to find the change in travel times. I'm going to start with time minimum. And time minimum, we can determine through 10,000. Why 10,000? Because it's 1 kilometers equal 10,000 kilometers equal 10,000 meters. So 10,000 meters over 2.0652 times 10 power 8 is 1. Okay. And the result is 4.8421 times 10 power minus 5 second. Okay. Or it is 48.421 okay, millisecond. And the next is T maximum. T maximum is 10,000 over this result 2.0647 times 10 power 8, and the result is 4.8432 times 10 power minus 5 second, or 48.432 millisecond. Okay, that one. And after that, we are going to find the difference. The difference in travel times, in times, okay. So it means this number, maximum minus the minimum. So delta T equal 48.432, okay, minus 48.421. And the result is as 0.011 millisecond or 11 nanosecond. And then delta T received is equal 11 nanosecond plus 1 nanosecond, according to this information, and it's equal 12 nanosecond. So the minimum received pulse duration is 12 nanosecond. Or 15, the linear absorption coefficients mu20 and mu100 for bone and muscle are shown for two incident X-ray energies of 20 kilo electron volt and 100 kilo electron volt. And this is the table Discuss with reference to the contrast in the final image, the difference between the use of 20 kilo electron volt or 100 kilo electron volt X-rays. I have provided for my explanations. Okay, this one, so I will not explain because I think this explanations is clearly right. Next, number B, 15B. Show that the intensity of the 20 kilo electron volt rays is half when traveling through 1 millimeters of bond, right? So I'm going to use the formula for the attenuation of X-rays. I equal I0 times e power minus mu x. I is the final intensity, I0 is the initial intensity, then mu is the linear absorption coefficient, 7.2 centimeter power minus 1, and x is the thickness of the material, 0.1 centimeters or 1 millimeters according to this information, right? So I'm going to substitute e power mu is 0.7, okay, yeah, 0.72 times 0.1 millimeters to centimeters, and it becomes I0 times 0.48675. So I equal I0 times 0.5, or I equal half I0, or I equal I0 half, like this. So we can conclude, or we can state that the intensity of the 20 kilo electron volt X-rays is half when traveling through 1 millimeters. This number 1 millimeters of bond. Okay. C. A 100 kilo electron volt X-ray beam goes through 2 centimeters of muscle and then 2 centimeters of bone. The density after passing through both layers is I. Calculate the intensity of ratio I over I0. Right. So the intensity after passing through muscle, I'm going to using IM. IM, it means the intensity after passing through muscle. This is I0 times e power minus 0.21 times 2. Okay. And then it is I0 times e power minus 0.42. So this is after muscle. Next, the intensity after passing through bone. This is muscle, and then bone. Yeah. So it is I equal Im times e power minus 0.24 times 2 equal, substitute this one, I0 e power minus 0.42, okay, times e power this one minus 0.2, 0.48, sorry, 48, because 24, 0.24 times 2, 48. It becomes I0 e power minus 0.42 plus 0.48 minus 0.90. So I over I0, this is the ratio, is 0. Sorry, I0 first, sorry, e power, so e power minus 0.90. So it means I over I0 equals 0.4066. I over I0, it is 0.41. Round off becomes 0.41. Or in percentage is 41%. So we can state that after passing through 2 centimeters of muscle and 2 centimeters of bone, the intensity of the 100 kilo electron volt X-ray beam is reduced to about 41% or 0.41 of its initial intensity. Okay, go on. Draw the variations in intensity of the beam with layer dip. Okay, this one from this diagram is the initial intensity. Okay, 2 centimeters layer of this bone. Okay, and we are going to sketch, draw. Okay, muscle and bone. So if this is 0 and this is 1, okay, it's starting from here. So this the coordinate point is 0.1, and when 2 This is, we can determine if 0 centimeters depth, the intensity, okay, the intensity uh, is the initial intensity, I0, or I0E. When 2 centimeters depth, okay, the intensity is I0 times 0.667. We can calculate this through the calculations I equal I0 times e power minus 0.21 times 2. So if 0.667 around here, okay, the coordinate point, and if 4 centimeters depth, uh, this one, if 4 centimeters, we already calculate this one, 0.46 or 0.47. Okay, this one there is to here, so 0.4 around here. So we can sketch like this. Yeah, like this one. Ultrasound imaging is usually performed at frequencies in the range of 2 to 20 megahertz. Outline why frequencies of 2.5 megahertz are used to image structures deep in the body, while frequency of 15 megahertz are used for structures close to the skin. I have provided my explanation. One, so no need for me to explain because if I will explain, uh, yeah, I need more time to explain, more duration. You may copy or you may add your opinion or your experiences into my explanations. But about this question, this is my opinion. Right. Continue. Explain the use of gel in ultrasound imaging. As well, I have provided my opinion. This you may copy or you may add something according to your opinion for this question. So I will not explain. I think this is clear. Next. 17, over 60 elements apart from hydrogen have been identified in the compositions of the sun. Explain how elements present in the sun are identified. I have provided also my explanations about this question. This one, this is my opinion. I have typing this provided. Okay, next is one. The temperature of the surface of the sun is 5,780 Kelvin. Calculate in nanometers. Lambda maximum for the spectrum of the sun. Right. I'm going to use the Venus displacement law, and it says that lambda maximum equal B over T. B is Venus constant. Venus constant is 2.898 times 10 power minus 3 meter Kelvin. T is temperature. So we can calculate 2.898 times 10 power minus 3 meter Kelvin over this number, 5,780 Kelvin. Okay. And if we calculate, the result is 5.014 times 10 power minus 7 meters. It's in meters, but we have to convert into nanometers. So 1 nanometer, I'm going to write here 1 nanometer, it is 10 power 9 meters. So it means lambda maximum, we have to calculate this number, we have to convert 5.014 times 10 power minus 7 times 10 power 9 nanometers. Okay, so this is, sorry, conversion actually 1 meter equal 10 power 9 nanometer. It becomes 5.014 times 10 squared, because minus 7 plus 9 nanometers, or 501.4 nanometers. That planets and comets orbit the sun distinguished with reference to their orbits between planets and comets. I have provided my opinion about this question. Which one? Elements heavier than hydrogen and helium exist in the universe. Outline how these heavier elements were formed. Also, I have provided these questions with my explanation, with my opinion. This is my opinion about this question. Okay, I think enough. Let's move to the next question. Number 18, Alpha Centauri A and B form the closest binary star system to the Earth. This binary star system is the third brightest stellar object in the night sky. Arcturus is the fourth brightest star in the night sky. Its apparent brightness is likely greater than that of the star Alpha Centauri A. Outline why the binary star system Alpha Centauri appears brighter than Arcturus. I have provided my opinion about this question. One, you may add something or you may copy this opinion. Right, next. Alpha Centauri A is a main sequence star. The following data are available. There's the data parallax angle of Alpha Centauri A is 0.76 arc-second. Luminosity of Alpha Centauri A is 5.7 times 10 power 26 watts. Luminosity of the sun is 3.8 times 10 power 26 watts. Show that the distance from Alpha Centauri A to our solar system is about 4 times 10 power 16 meters. Right, I'm going to use the formula D equal 1 over P. D is distance to the star, and P is the parallax angle. So it means if we substitute this information, we can have D equal 1 over 0.6. arc cycle. And if you calculate, the result is 1.315789. Okay, the unit is parsec. Okay, and if you uh, continue to round off, I would like to round off 1.316 parsec. Okay, next. The unit is in meter. It means we are going to convert 1.316 parsecs into meters. Just information that 1 parsec is equal to 3.086 times 10 power 16 meters. So it means if we convert this number into meters, we have to calculate this number with this number. 1.316 times 3.086 times 10 power 16 meters. And we're going to have the result 4.06 times 10 power 16 meters. Round off becomes 4 times 10 power 16 meters. But for the next calculation, I'm going to use this number 4.06. Right. Calculate the apparent brightness of Alpha Centauri A. So just now, number one, proof that the distance from Alpha Centauri A to our solar system is about 4 times 10 power 16 meters. Now this one, calculate the apparent brightness of Alpha Centauri A. We can use the formula for calculate flux, that flux equal L over 4 pi d squared. Okay. Uh, F apparent brightness or flux, this one. L is the luminosity of Alpha Centauri, 5.7 times 10 power 26, if not mistaken. Okay. One luminosity of Alpha Centauri. Okay, and D is the distance to Alpha Centauri. So we can calculate, becomes F equal 5.7 times 10 power 26 watts over 4 times 22 over 7 pi. So pi is 22 over 7 times 4 is d squared, 0.06, because this one times 10 power 16. Okay, squared. So the unit m become squared as well. So it's going to be F equal, if you calculate this, the result is 2.7536. On my calculator like this, times 10 power minus 8. Okay. Watts per meter squared. Round off becomes 2.75 times 10 power minus 8 watts per meter squared. So the apparent brightness of Alpha Centauri A is approximately 2.75 times 10 power minus 8 watts per meter squared. Show that the mass of Alpha Centauri A is 1.1. M is the mass of the sun. Where this symbol is the symbol for mass of the sun. Right. So the mass and luminosity relation, the formula is given by this equation. luminosity over luminosity of the sun. This is luminosity of the star equal m mass over mass of the sun power a. Right. L is the luminosity of the star, Alpha Centauri star. This one. And then this symbol is luminosity of the sun. M is mass of the star, Alpha Centauri star. And then this symbol is a symbol of mass of the sun. A is a constant number, range between 3 and 4. So I'm going to take in 3.5. Right. So if we substitute this number, it's going to be, wait, M over mass of sun power 3.5 equal L is 5.7 times 10 power 26 over mass of the sun is 3.8 10 power 26. So if you calculate M over M the sun, mass of the sun, it equal this is 1.5 power 1 over 3.5. That one. So and if you calculate n over mass of Alpha Centauri A over compared with mass of Sun, it's equal. I have calculated this 1.12. Round off becomes 1.1. So it means m or mass of Alpha Centauri A equal 1.1 mass of the sun. So we can state that the mass of Alpha Centauri is or equal 1.1 mass of the sun. That one. Next, on the HR diagram, Hertzsprung-Russell diagram, plot with an X the positions of Alpha Centauri A. Okay. Alpha Centauri A is if L star over L sun is 1.5, it means we can determine this is 10 point, if we can 10.15, around here, is around here, the locations, and then draw the most likely future evolutionary path of Alpha Centauri A, labeling the two main regions of this path. Right. When Alpha Centauri A houses the hydrogen in its core, it will expand into a red giant. So the core will contract and heat up, and the outer layers will expand and cool. So the stars will cooler, but more luminous. So it means the effect or the implication for this diagram, luminosity will be higher. This luminosity will be higher to upwards, and the surface temperature will be lower. Lower, it means to the right. Okay, it means around here. Okay. Proxima Centauri is main sequence star with a mass 0.12 mass of the sun. Compare The times for which Proxima Centauri and Alpha Centauri A are main sequence star. The comparison can be expressed by this expression that T is time, Tp over T alpha. This is Tp for Proxima Centauri. This is for Alpha Centauri A. Okay, it equal M alpha over M P power A minus 1. A is 3.5. So it's going to be T P over T alpha is equal 1.12 over 0.12 power 0.5 minus 1 power 2.5. 1. If you calculate T over T alpha, if you divide it, becomes 28 third 2.5 power 2.5, and the result is 2.66, sorry, 266, not 2 point, 266, sorry, I have to move here. So Tp over T alpha equal 266.13. Okay, round off becomes 270. So the Proxima Centaurs, we can say that the Proxima Centauri's main sequence lifetime is roughly 270. So times 270 times longer than Alpha Centauri A. So actually we can writing this result becomes Tp equal 270 T alpha, like that. Again, we can state like this. Next, explain the relationship between binary star systems and the type 1A supernovae. I have provided my explanations about this one, this question one, and F outlined how type 1A supernova can be used to measure very large astronomical distance. As well, I have provided this, and if you want to calculate the distance, you can use this formula. I'm going to writing here the formula: square root of absolute luminosity over 4 pi times apparent brightness. So the formula. Okay. 19. Cosmic microwave background (CMB) radiation was discovered more than 50 years ago. State one characteristic of CMB radiations. I have provided as well my explanation about this. Okay. CMB, it means cosmic microwave background. Okay. And question B, outline the significance of CMB radiations in relation to a Big Bang model. I have provided also one. Okay, if you look here, that BB is Big Bang. Okay. CMB is a cosmic microwave background. Right, let's continue. And the question C, state and explain one additional piece of evidence for the Big Bang model. I have provided as well. So one, you may copy or you may add your opinion on this explanation, this briefly explanation. Next, number 20. Quasars are bright celestial objects which show very large redshifts. Show that the light from a quasar with a redshift of 7.5 was emitted when the universe was about 12% of its current size, right? We can use scale factor rule. It says that R over R0 equals Z plus 1. Okay, R is scale factor. So it becomes R over R0 equals 7.5 because Z is 7.5 plus 1. So R over R0 equal 8.5. It means R0 is 1 over 8.5 R. And if we calculate 1 over 8.5 is 0.1176 R. R0 equal 0.118 R. Or in percentage, it is 11.8% R. Or R0 equal 12% R. This one. 21. The graph shows possible models for the fate of the universe. This is the graph. This is the axis for time, and this is the cosmic scale factor axis. Comment on the value of the density of the universe for line B. So this line B. Line B is line for the value of density. Look, actually, this is not B is not the straight line. This is a curve because look the line, this point, okay, and this line to the curve A. Actually, this line is asymptotic, okay, for the line A. Asymptotic meaning it has no intercept point. So line B has no intercept point with curve A. I'm going to writing here that it corresponds to, wait, I have to fix this. Okay, corresponds to the critical density. Okay, and so the critical density point on this point, and actually line B is asymptote. Okay, so the curve becomes asymptote, asym, asymptotic to the time axis. Okay, this one. This is for axis for time. I mean, okay. B. Uh, it means it has no intercept point. If asymptote. State and explain which line is related to the concept of dark energy. If you look this line B as well as C, okay, B and C similar, but different with D. Okay. So D is the different curve and the questions which line? D line. Okay. D line. Why? Because this graph, this line or graph, okay, is identified as accelerated universe. Okay.